Hello, everyone, and welcome back to the video tutorial series of modeling silicate chemical weathering in BioRT-HBV. In previous videos, we have talked about setting up the reaction network, creating input files, and running the model. In this video, I will show you how BioRT-HBV silicate weathering model results can change as we change 4 different input parameters in the model. We will change each parameter separately and view the different results as time series. If we review our base case reaction rate equation, we can remember that we are starting with the simplified rate law, R equals K times A. We will begin with our base case, in which the reaction rate will not change as a function of temperature, soil moisture, or water table depth, but is equal to just the reaction rate constant times the surface area. You can change any of the parameters that we talk about in this video by going to the cine.txt file and changing the parameter values and just saving the file. I've chosen 4 of the most important parameters to change for a silicate weathering model: reaction rate K, specific surface area, Q10 from the temperature sensitivity term, and SW_EXP, or soil moisture exponent, from the soil moisture sensitivity term. First, let's look at our base case parameter values. I have chosen to model the base case with the following parameter values. You might remember that by setting Q10 to 1 and the SW_EXP to 0, I've made the reaction rate insensitive to temperature and soil moisture. Also, note that I've used the same parameters for our solid anorthite in both the shallow and the deep zones. Here is a screenshot of the cine.txt file with the parameters boxed here in red. We've got the reaction rate constant K in log form, specific surface area, Q10, and SW_EXP. These 4 parameters will all have a significant effect on the reaction rate for the silicate weathering and on the modeled shallow and deep zone concentrations for the solute of interest released in our reaction, and thus will have a big impact on the stream concentrations for that solute. Here, I've plotted the time series of the results from the base case, showing the modeled and measured dissolved calcium, and compared it to the time series of the modeled hydrology from the calibrated HBV light model. The modeled calcium in the shallow zone, deep zone, and in the stream are shown as solid lines in shades of red. I can see here some general trends in the base case and how it's similar and how it deviates from the measured stream concentrations of calcium, shown here as gray circles. I can see in this sort of medium red the trends and the overall data for the modeled calcium concentrations in the stream, and how it has downward falling peaks of calcium concentration during the peak stream flow or when there's a rainfall event, and higher values during drier periods, which is base flow conditions. Also, I'm seeing that the measured calcium is showing much more seasonal variation in the higher values, especially during dry periods, which I interpret as coming from the deeper zone during base flow conditions. In order to manually calibrate this model to become more like the measured data, I would want to understand how each parameter will affect the modeled concentrations of calcium in each zone. And we'll begin by changing parameter values one at a time and viewing those results. Next, let's take a look at the first of our 4 chosen parameters to change. Let's see how changing the value will change the model results in the 2 zones and the stream. First, let's try changing rate constant K. Our simplified reaction rate equation is R equals K times A. So we expect that the reaction rate will decrease with a decrease in K. We will change the K value from -11 to -12, which is a decrease for this logarithmic value by an order of magnitude. In order to change the parameter, I recommend copying your base case input folder and renaming it after your new change, and then in your new input folder, change the parameter value in the cine.txt file. Here is the cine.txt file. And here is the upper zone initial concentrations and the parameter values, and the lower zone initial concentrations and parameter values. So go ahead when you're changing the parameter and just edit the values. So this is the log K value, -11 to -12 for the upper zone. And in the lower zone, here's again the log K value. The log K is the tag here, and then it's followed by the value. And just simply save that file, close the file, and you can rerun your model. This way, when you run the new case, you'll have the name of the new input folder, which will include that change that you made. And that's going to mean that your results file will also show the case name, and the case name shows the change that you made. That's going to make keeping track of the results and your manual calibration steps that much easier. Here I've plotted the base case reaction rates for the shallow and deep zones in shades of red, and the reaction rates for the case with a decreased K in green dashed lines. We see that, as expected, the new case reaction rates are much lower than the base case reaction rates. Next, let's look at the concentrations in the stream, shallow, and deeper zones for the base case and the lower K case. The base case, again, is in shades of red with the measured data in the gray circles. And the new case is in shades of green with dashed lines. As expected, based on the reaction rates and the reaction rate equation, the concentrations in our new case are all lower in all of the zones. And interestingly, the peaks in the deeper zone are also more modulated with lower variation in maximum and minimum values. For our next case, let's alter the specific surface area. We will alter the reaction surface area in the reaction rate equation by changing the SSA value, or specific surface area. That parameter, along with the volume fraction parameter, determines the reaction surface area in the model code. We are increasing the SSA from 0.01 to 0.01, which is an increase of 1 order of magnitude. Looking at the concentration results with the new results in shades of green, we can see that the increase in SSA must have increased the reaction rates for anorthite weathering, because we see increase in the concentration here in all 3 zones. And that's as expected. The next parameter to look at is Q10. Q10 is a parameter that represents how much a reaction rate changes with a change in temperature. The new concentration results show us that going from 0 to 0.1 to 0.5 Q10 increases concentrations in all of the zones. Lastly, let's look at the soil moisture sensitivity and change the parameter for SW_EXB from 0 to 0.7. Here, I've plotted the results stacked with the modeled hydrology in shades of blue. We can see that our changes have lowered the concentrations. Here, the new case is in the green shades in all of the zones. Note that the best way to see what each of these parameter effects can be is to make multiple cases for each parameter, altering the values up and down, and compare the resulting reaction rates and concentrations and the modeled hydrology side by side. That's it for this video, the last in the silicate weathering tutorial series. Please check out the other tutorial video series to learn how to represent other processes in the BioRT-HBV reactive transport model and thank you.